Okay, the purpose of this video would be to review some of the turning functions that we learned in the first lathe class, and also the C operations that we were getting into in the advanced lathe class on this part that you've already turned in and got a grade for. But what would be next would be this part. The assignment is to actually just write a program for it and using G71 for the OD turning, G71 for the boring cycle or the ID turning, and C-axis for all other features, using a parting tool to chamfer the back and cut down to 3.5. So the nice thing about this is it's an imaginary part, so we don't have to worry about digging up material or anything for it or how we're going to hold it. We'll just assume that the front of the part is this pointing in. But before we get into that, let's go ahead and review the G71 and the G72 cycles. And I'm pretty sure I gave you this file with, this is the SL series workbook that we used in the old, in the original CNC lathe class. So let's talk a little bit about the G71 and G70 OD Type 1 roughing and finishing. And we talked about this a little bit in the Little Slugger first video, but we'll just review it again. So this would be your program number. By the way, you're free to copy and paste these into a text file, and that way you won't have to type all of this, all of these codes in, and you'll have a pretty good framework for how to write your program. And all you'll really have to do is change the geometry here. Makes it really super simple. Okay, so let's talk about the G71 cycle first. G71 is for turning cycles where, notice these arrows are moving in a Z minus direction. So most of your roughing will be in a Z minus vector or direction. So T101, first of all, G28 will zero out the machine in X and Z. T101 also calls out an OD tool with a .032 tool nose radius, TNR. G50 S3000, this sets the RPM limit at 3000 because I'm going to be using constant surface feet. We're going to tell it G97 S450 M3. What does this do? No, I don't want to ask Cortana. So we're going to G97 is constant surface feet off, 450 RPM, turn on the spindle. G54 G0 X3.1 Z.1 rapids the Z and the X down to the front of the part, turns on the coolant. By the way, anything going this way is a Z value. Anything from the center out is an X, and we always program X on the diameter and Z simply on the length. Okay, once we have our tool positioned, we're going to go ahead and turn our constant surface feet on with this G70 or G96 S370. So now we're not turning 370 RPM, we're now turning 370 surface feet. So this RPM will now change based on where the tool is in X. So it's going to position Z to the face of the part, and notice we're at 3.1, so which that would be clearance. So we're going to wrap it right down. And just like the ball bat, first thing we're going to do is we're going to face the front of the part. We're going to tell it G1 and G0 mean the same thing for milling and turning. So, well, little things are bothering me here. So, feed down to X minus .062, So the reason we go 62 thousandths past center is because of the tool nose radius being 0.032. So we have to compensate for that. Otherwise, there will be a little remnant on the front of this part. So that's why we feed just past center. We feed, notice it's 0.062, which is twice the tool nose radius, and that's because everything's programmed on the diameter on X. So, okay, after we face down to center, we rapid to X3.1, Z.1, which would be kind of the beginning point here. By the way, this is on page 84. This is a really great example that you can copy and paste to write all of your programs for the turning part. So this G71 cycle, it's going to be pretty much the same for most anything you program. There's no geometry in here. All it's doing is calling out a P and a Q value, which just actually relates to the N values. Think of them as bookends that kind of hold the geometry, they nest the geometry of the part in here, in between them. So the geometry of the part is simply all these points that will create a single block of information in the program. So G71 turns on OD roughing, or type 1 roughing, because you can use G71 for OD and ID, because we'll explore that in a minute. So P10, Q20, read lines N10 through N20. Q.01, W.005. Again, this is how much material will be left on the part for the finishing operation down here in the G70 cycle. So again, U is doubled because it's on X, and we're really only cutting 5 per side, which ends up being 10 on the diameter. D.125, which is our each roughing pass, will be taking 125 thousandths. And the beauty of this is the roughing cycle will actually create steps all the way down and take equal passes. So you always want to use this when possible. This is not specific to Haas. Finite controls do this as well. So N10, G0, X.325. So you have to do it exactly like this example, or it will throw up a non-monotonous code, which is the dreaded non-monotonous code, and drives people crazy. So if you just follow the example just like this, and you will have no trouble. So we wrap it down in X, start the geometry, then we feed into 0, Z0 at 10 thousandths per rev. And then all it's doing here is we're playing connect the dots, feeding up to 425 and so forth. And then it does a G3, X1 inch, Z minus 0.5, R point 125. Now notice again that the start point in X is 0.250 away from the target dimension, the X1.0 for the radius. And this is because everything is still on the diameter. Everything's on the diameter. And we're going to feed down to Z minus 0.5. And then anytime you get a linear interpolation for a G3 or a circular interpolation, you have to follow the next line up with either a G1. If you're not going to cut any, continue to cut circles, it needs to be turned. The G1 needs to be reactivated because G3 is modal, and it will stay in G3 until you tell it otherwise. So G2 is turning the. Oh, by the way, the G42 up here, that turns on tool nose compensation right. So the tool is to the right of the part as it's moving in the Z minus direction. Okay, so follows through with the geometry, and then N20, G40 turns off the tool nose compensation. We're going to wrap it out And so your program should be just like this, where you wrap it out in X and leave it. And then that way it will know to go back and start. It'll automatically move Z back to the start point. This start point right here. That's where it will wind up. So after that's done, you simply give it a G70 P10Q20, and then it'll go back and repeat all this information one time and cut a finish pass. Okay, then we're going to go turn the constant surface feet off at 450 RPM. So now when you see G97, it's now RPM and not feet per minute. And turn off the coolant, M9, take the tool home, and M30 in the program. So let's skip past this. That was page 84. That's going to be a really good example for you to use on, this is our actual programming project, except I'm wrong about that, because I'm going to actually use the G72. Let me skip on past here. Or G72. Sorry about this. So G72 is the same thing. All the positioning, everything's the same, except G72 is more of when you want to cut in X minus. So since the majority of our part is going to be cutting in X from the raw material, say you've got a say this material is 4.250, so you'll face it. Let's see, with G72 you don't have to face it. That's one thing different. So they just come in, turn on your spindle limiter, G54, position it, and since notice how they are positioned at X3.1, Z.1, and then they wrap it into Z minus 1.6. So they're actually going to start the cut up here and make the cut this way, which is what you'll do on your programming assignment. Nope, not that one. You'll wrap it down here and cut this way, and just like they do in this example on page 96. So you can actually copy and paste all this into your text file and just change the geometry, and you'll be pretty close to having that done. So then the other thing you need to do with the turning is this boring cycle, okay? Be sure to drill this out. The drilling cycle is in the same original manual. So just use a G80 or G73 or G83, something like that to drill that out to just under 500. And then you'll use a boring cycle, G71 boring cycle, to bore that out, which is on page. Got a perfect example of it here that you can copy and paste and just change the geometry right here. This will be the boring cycle. Everything's, like I say, the same. A lot of this is the same as far as positioning. Notice they're at 0.9, Z.1. And let's see, X.9, Z.1. And they, instead of being way up here, they're at the smaller part of the hole for where they start their cycle. Wrap it to start point below the ID stock diameter. So this time we're going to use same G71 because we're cutting, most of our cuts are in the Z minus vector. Get rid of that. Or direction. Now, one thing different is the tool nose compensation will be G41 with this cycle because the tool is to the left of the part as it's moving in Z minus. So that's a distinction. And then you just follow your geometry on down, because once you turn on your tool nose compensation, you don't care about the radius of this tool anymore. You just program it just as it's an imaginary dead sharp point. Okay, so just copy and paste that. So that's on page 88. So that will take care of the turning elements of your programming project. So now we'll go into the axial and radial milling, and for that I will be sending you with this file this lathe series training manual. The good thing about this manual is it's super short, and it really just has some really great information to help you understand the process of what we're looking at right now for this project. So on page 2, this pretty clearly describes the axial, and I always think of not axle rows particularly, but I always think of the axle of a car being in line with the spindle. So that's kind of how I remember axle to axial is kind of your face. You know, your tool center is on the same center as your spindle, so it's pointing at it, just like this diagram shows. Radial is for drilling holes and milling on the outside diameter, just as it shows here. So for example, on our C-axis programming project, this will be an axial tool. These will be axial tools. Now here's a tip. This has to be trigged out, so you'll have to index your H or C axis to where this is actually at 12 o'clock, or here, and then you have to. I gave you the two sides of the triangle, and you have to trig out the hypotenuse. That's pretty easily done with a trig app on your phone. So let's see, where were we? These slots and holes will be done with radial tools, radial tool paths. And so it's pretty simple when you break it down that way. I had some students have some question about this line right here. That's actually just showing this slot on the side. So to get this programmed, oops, they have some really great examples. You really only need to look at a couple different examples, but let's just talk about go through the book here a little bit. On page 3, it shows you how to set up this is setting up a radial tool, and to do it properly there are actually a couple little set screws on either side of the slot, and you're supposed to put a dowel pin in the chuck of the axial tool or the radial tool to make sure it's properly indicated. And what I've found is that most of the radial tools have the set screws kind of set, so I haven't spent a whole lot of time indicating them. It's kind of up to you. It'd be good to practice it. It just kind of depends on how much time you have. Other than that, this little bolt, I think it's like an 8mm or a 10mm hex wrench. You just unscrew it, and there's a little gear on the post of this tool. It just lets it come right out. You probably remember that. So the axial and radial tools are pretty much the same. This page 5 kind of goes through the procedure for setting tool offsets. It's just like setting off OD or ID turn tools. One difference is for radial tools, sometimes if you say you have, let's get back up here so you can kind of, say you have a drill like this on the radial, and it's kind of up to you. It just all depends how you want to program. Say this is a 1/2 inch drill. Once you touch off the front of it with the side of the drill, you want to probably add another 1/4 inch to the Z minus, and what that will do is put the exact point of the drill on the edge of the part, so you don't have to figure that in to the program. Now I will say at Democo, we program from the edge of the drill, and that way it takes less time to set up. So it's I won't hold you accountable either way. Just you might type into your program in parentheses how that Z offset is set for your radial tools. So keep in mind the Haas Live tooling is designed for medium duty, so nothing bigger than 3/4 on mild steel. Maximum live tooling drive speed is 3,000 RPM. Just kind of going through this a little bit with you. This is a nice diagram of how the live tooling looks. Notice this little rat gear. When you screw in the what do they call it, a VDL? I think it's named after some German, VDI, here we go. It's actually named after some German engineer that invented this. I Googled that one day. So anyway, this is a little crown gear that locks into the drive mechanism. So you really just have two options on the live tooling. You got face milling or axial, and you got side milling or radial. So we've always called it face milling or side milling. Probably the correct thing is axial and radial. I'm going to scroll on down here. Ignore all of this on page 8. Just ignore it. Okay, so live tooling code. This is something you may want to go ahead and print off on page 9 here. It gives you all the M codes you will need to do your programming. So you see these M100s codes and you start going, oh my word, I'll never remember all this. So you don't have to. And the fact is that different manufacturers all have different M and G codes for their live tooling. So usually I will have some program examples in my control, and then I'll just copy and paste those program examples to make one big program, and then just change the geometry just like I'm having you do for creating this this imaginary part. So you can read over these. Some of it's pretty logical. Now the G98 and G99, that's something we're going to be switching back and forth here, because for all your turning you want to use G99. For all your milling, so that's inches per rev, G99. Milling is G98, or inches per minute. Okay, so that'll get you in trouble a little bit if you tell it 4 inches per rev. It's probably going to exceed. It's going to move real fast at 3,000 RPM, 4 inches per rev. So that's something you have to really start watching with the live tooling. So moving on here. This is also something that you have to take into consideration on page 10 is your work plane selection. So, anything on your side milling. Now this G18, that's going to be pretty much for using the y-axis, and we're not even talking about that yet. We're just talking about c-axis operations, simple c-axis operations, and kind of a turning review. So you'll be kind of using G18 and G19. I think G17 is the Y. Above illustration shows the G17, 18, 19 planes for throwing radii on a lathe. So it's all about cutting radius. The default on a lathe is G18 for that. So when you're in turning mode, you're going to be in G18. Don't forget that. So the radial shown above is along the y-axis. Radial cross drilling can cycles need to be in G19. So we'll be either in this entire project, oops, darn it. We'll either be in G18 or G19. I just X'd out of my project. So I'm going to open it back up again. Bear with me. Open, get a tour of my file organization system for 1 second. Let's see. Programming only projects. Here we go. So there's going to be like 3 of these. And the idea is that it helps me to have an idea of where you're at with the programming. Here we go. Okay, got it back. So, back to the Haas Live tool. And this diagram on page 11 kind of illustrates if you tell the spindle, which is actually your C-axis, is your spindle. It's just a true 4th axis. If you tell it 0, it'll be oriented this way. C90 moves clockwise 90. So plus moves clockwise, minus moves counterclockwise. Okay. M19, M119, that's your secondary spindle. We'll just completely ignore that. So M19, go back to your M codes. This is why it's good to print them off so you can just kind of have them by your side here. Orient spindle. You can also say G28, C0, or H0. So H is incremental for C, for the C axis. So just like UVW, XYZ, H corresponds with C. All right, now this page here is wonderful, page 12. Will tell you all your can cycles for working on your face. So your face working cycles will be this hole, these slots. It's really pretty simple programming. You just got to throw out the right command there. So manual slots, X and C axis milling, you'll be in G18 with a G98 feed rate. And so your face working cycles is your axial, cross working cycles radial. Now here's a great example of a program for face milling with live tools. So you can copy and paste this into your program, your text file, and then you'll have your hole drill. Just change, what tool you're using, your X value, your C value. Let's just kind of go through this for a second. G0, X3.0, Z.1, just rapiding into position. G98 inches per minute. So some of these codes are now pretty important to the proper function of your program. So M19, P0. You can also say G28, C0, M14 clamps the spindle. Now turning the RPM on with your live tooling is a little different. It's instead of M3, it's M133, and the P2000 means it's the same as S2000, so 2000 RPM. It is actually feeding in and rapiding out. One thing I don't like about this example is it doesn't use a drill cycle. You could use a G83. Maybe there's some better examples on down here. There's also a ton of examples on the internet for Haas live tooling. Okay, here we go. Same example using C-axis with G81 code instead of M19, which I would prefer this because it's easier. So tool 101, tool calls up the same. G18 is inches, or is your work plane, X and Z. Still using G54, so don't forget that. G98 turns on your inches per minute, and when 154 is, you have to actually turn the C-axis on, because sometimes it's a spindle for turning and sometimes it's a C-axis for milling or indexing. So you'll actually not be at C0 on this. You will have to calculate what that angle is going to be. I don't know off the top of my head. Should be able to calculate that with all the information I've given you. So this is a G81, so it's just going to peck it. And then if you give it a C120 and a C240, it's just like a canned cycle. I think we're having a little bit of a problem with that. On some of them we're having to recall the canned cycle out twice, but it'll go ahead and cut the other two holes. So if you write your program like that, I'll call that good. Same deal with G83 with a Q. G83 would be a full retract pack for a deeper hole. So all these you can copy and paste into your text file. Don't need rigid tapping because there's no rigid tapping on the project. There's no tapped holes. Ignore the fine spindle control, ignore all that. Page 16, page 17, ignore it. Also page 18, this G5, we're not using any of this, so ignore page 18. Now page 19 is a great example of axial or face milling that you can use that example to mill these three slots. So just copy and paste it into your text file and just change your geometry. So all your tool call outs will be in there. I'm not too worried about which tools you use, tool number wise, because as long as the program would cut the part if the tools were in that turret. So all these codes are pretty much in the book there. So that's a good idea, kind of to print them out. Have them right by you while you're writing your program. So M133, P2000, that's how we turn on the live tooling RPM. M154, engage C-axis. They spelled axis wrong. Typical textbook. So they're orienting C to 0. So you would position, for example, your end mill at 0. And what I would do is just G1 feed up this way, and then I would say G0 H minus 90, and then feed back to center and say G0 H minus 90 and feed back up. So you'll just be feeding back up and down while rotating the C-axis on that. Same with these slots, except that'll be more of a radial milling. In other words, you'll leave the end mill here and just rotate the part, moving back and forth. And here's a simple cam cut with X and Z. So these are all just real simple examples of the program. Let's see, ignore that. We'll get into this after we do the Y project. We'll get into the G112. So ignore this for now. Ignore that. Ignore that. So here is your perfect radial cross milling and drilling example on page 29. So use this example to mill your slots and drill your holes on the outer diameter. So the codes, T101 is pretty much the same for everything. It's calling out the tool number and the offset. G19 is your work plane select. That's at the beginning of the book. G98, inches per minute. M154, engage C-axis. So we're now in G54, we're rapiding to position with X, C, and Y. Well, ignore the Y part. We're not using Y on our project yet. We will be on the next one. But first we got to get the C thing down. So G97, P1500, M133. So for some reason they're giving it a surface feet off here, which is fine. But P1500 is the RPM and turning on the live tooling spindle. M8 turns on the coolant. G0 is rapiding the tool into position, because remember, even when we're drilling, we're on the diameter. So if this is like 2 inches, you have to tell, and this is 3 inches. It's weird because it's different, but you have to tell it to drill to 2 inches, even though you're only drilling 1 inch, or you're only drilling a half. If this diameter is 3 inches, this diameter is 2 inches. You're only drilling a ½ inch deep, but you're going to have to tell it to drill 1 inch. You're going to have to tell it to drill to 2 inches, whatever that diameter is. So G19, they're kind of duplicitous here. I don't think you have to give it a G19 twice because it's modal. G75 is a radial peck cycle, which is like, it will not do a full retract, but it will just peck, 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 peck. And so the I is the pecking frequency. So it's going to peck every 250 thousandths at 6 inches per minute. So notice that they give it a G0 C180, and then they call it out again. It's not letting me highlight it either. Then they call it out again. This is kind of how we had to do it in class, if I remember right. So, but and also C270. Okay, they're going on C. So the C is actually rotating the stock and the spindle. So then after that, we give no need to give it a G80. That's just G0 cancels out all your drilling cycles. And we wrap it out, turn off the coolant, and 135 turns off the spindle, and 155 disengages C-axis. So it's one of those things that if you engage something in the program, you're probably going to have to disengage it too and turn it off. So see this G0, G28, H0? Think of it like when we home out a milling machine, we do that in incremental. And what this does is it takes it to 0 the quickest way. So say it was wound up to C380, sometimes it'll be C1 valve. I've seen fourth axes get wound up to like 1,000 degrees. And then if you tell it G0, G28, C0, it'll sit there and spin to unwind. Whereas if you tell it H, it'll incrementally go to the 0 as quickly as the fastest route. So that's why they use H there. That's the way I would prefer to do it. And then we're rapiding out into the clear. Ignore the Y because we're not using Y yet. This is just a C-axis lathe. So X, Z, and C-axis lathe. So most lathes will either be X and Z, X, Z, and C, or X, Z, C, and Y. So if it has a Y-axis, it'll have a C-axis as well. So G18 puts it back in turning, the plane in turn mode. G99. So this is a safe thing here. By putting it in turning mode and putting it back in inches per rev, we're removing the possibility of telling it to go 4 inches per rev at 1,000, 3,000 RPM, like we were talking to before, or talking about before. So anyway, here's a little list of your radial can cycles. This is on page 29, by the way, so that's a really good copy-paste thing for all of your radial cycles on it. Notice the similarities, okay? The other thing about this project is, okay, ignore this. We're not using y-axis yet. Is that I have the students submit it to me. I make comments on the paper, submit it back to you, and then we pass it back and forth, and we can do this with email. Pass it back and forth until you get 100% on the project. And I believe, yes, this is worth 50 points. So it's a lot of points, just a little bit less than a part that you would hand me. The nice thing about this is you can do it at home. Work on it at home. And I like this kind of assignment because if a student has to miss class, they can do a lot of this at home, but if they're at class, they don't have to do the homework either. So, okay, ignore the radial tapping. It's just the same. It's just a different. Everything's the same here. It's just a different can cycle. The G195. I mean, it's all that changes. So much of this is repetition and redundant that once you get the idea. Alright, I like this diagram on page 39 because it really shows a nice cutaway of the lathe, because when we start using the y-axis, it starts getting really confusing. Seems simple enough, but it starts getting really confusing. So if you're looking straight at the tool turret, X movement's this way, Y movement is this way, which we're not really getting into yet. But so right now we're just using X, C, and C. Gives you a nice visual. Now this just talks about the limits of the y-axis being plus or minus 2 inches off center. And we're not going to get into that too much because the y-axis is a next project, and I wanted to kind of talk to you about the C first. Now ignore all of this. We did not do this homework, so ignore that. And ignore this. We don't have to do this because this is for older lathes. And that's pretty much it. So I'm open for, if you have questions, try to make them as specific as possible, and that will help me get you up to speed with where you're at. And we'll call that a wrap on this, and I'll be starting to work on the y-axis programming project and probably the bat handle. But I wanted you to have something you could work on at home, and if you wanted to. But I'll send this to you here.